Spring and mass systems, yay! So, not such a hard concept, but it's one of those things that we're spelling out. So essentially, you know, everyone goes, what's a spring? And we think coil spring, leaf spring. But basically what a spring is something that exerts a force. And, you know, we say force. Well, what's a force? Yeah, here we go. We got a 30-pound weight. So if I go up, I go down. Gravity pulls 30 pounds up and down. There's a motion, and there's a force that, you know, follows that motion. So, you know, we'll draw a coil spring, right? Here's our coil spring. You know, the top is fixed, bottom moves up and down. Well, you move the coil spring up, it exerts, we'll say, 10 pounds down initially. You move it up a little more. In this case, it's a, you know, straight rate spring, so it's 10 pounds for every inch. You go up another pound, another inch, it's another 10 pounds, so it takes 20 pounds to move 2 inches, 10 pounds to move 1 inch. Not such a hard concept. Now, springs don't have to be straight rate. There's springs that have no rate, you know. If we had an air spring, for instance, right? You know, kind of a funny example because air springs usually don't have, you know, that kind of rate at all. Air springs have the other problem, but we would have you know, an air cylinder, and it was connected to you know, an air volume that was infinitely large, and you know, there's 10 pounds of, you know, air pressure in the shock and the piston, you know, areas, you know, 1 square inch. It's 10 pounds per square inch, 1 square inch. As you go up and down, regardless of how much travel, it only ever takes 10 pounds because, you know, the volume you're moving is negligible compared to this giant, you know, air volume. So this is a spring with no rate, you know, and then you can have springs that have rising rates. So, you know, we all think about leaf springs. Most trucks have a leaf spring, or they used to at least, in the back. And what is a leaf spring, you know? Little shackles. And it's actually a bunch of springs, you know, stacked together. And, you know, there's your axle and your axle hangers. So a leaf spring, you know, when you first start moving up, you know, you're really not flexing, you know, these 2 springs, you're only flexing the 1 spring. So because you have appreciably thicker spring mass, you know, in with the extra 2 leaves, right off the way, most of your flex is just in this one little leaf. And then, you know, so the first, you know, again, the first inch of travel may only take 10 pounds to move it. But when you start having to flex these big, you know, springs, you know, the first inch of travel takes 10 pounds. The next inch of travel takes 50 pounds because there's a rising rate. And then after that, it may take 150 pounds to go another inch. That's a rising rate spring. But essentially, a spring is just something that, you know, there's motion and there's a corresponding force with the motion. Not that complicated. I'm sure you guys are all well aware, but you still want to, you know, appreciate what's going on. You know, of course, the funny thing with a spring is, just like, you know, think about a light pole. Everybody's seen a light pole in a storm. And, you know, what does it do? Hell, forget about a storm. Just go up to a light pole, an aluminum light pole, and start shaking it. And, you know, even a little kid can get, you know, the light pole wobble back pretty appreciably. With just a little kid. Boom, boom, boom. And that's because a spring has a natural frequency. A spring, you know, has very little a metal spring at least, has very little damping to it. So, if you feed that natural frequency to the spring, you know, just like a tuning fork, you can get it to wobble further and further out of the way because there's very little damping. The only damping in a spring is really, you know, the material itself has some amount of, you know, inherent damping as it shifts, you know, the little molecules, you know, do the little grind, bump and grind, but it's very little. So for all practical purposes, springs don't have damping. So if you drive a vehicle and there's no damping, we all know what's going to happen with the vehicle. It's going to bounce down the road, you know. You're going down the roadway, and you got your little car, and it's got its spring. Hits a bump, and the car, waddles forward, waddles back, bouncy, 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 like a boat, and I got my boat videos. So you hit that first bump, and all of a sudden the front of the car is bouncing up and down, bouncing up and down, bouncing up and down. Like a little kid, sitting on the toy in the park with the coil spring where they wobble back and forth in a little pony or whatever it is. Springs don't have dampening. They bounce and they wobble, and that's what it is. I don't know why I had to draw this, but we get the point. So, how do we stop that? Well, obviously, cars have shocks, and what is a damper? They're not shocks; they're dampers. We think of a damper as they're usually fluid filled, and that's because where a spring has motion with force resistance, but a spring, a theoretical spring doesn't care about velocity. In real life, obviously they do, but there's a reason why Formula 1 cars will do Mac valve springs. But getting back to that's actually not relevant. So a damper, and there's friction dampers, there's fluid dampers, but we'll start with just your traditional fluid orifice damper. The reason we have them on cars, and trucks, and boats and things is that when the damper moves, it's fluid has to flow either around the piston or through the piston, but a damper provides resistance to motion. Well, the resistance to motion and the spring mass system, they work together. So, there's lots of, engineering talk about balanced dampers, a perfectly balanced spring mass system. Or I should say spring damper mass system. They all work together. So, for givens, we'll put a mass on top of this, right? Mass is M. We'll knock it down. The collar, we'll put our coil spring. And then there's, we talk about balanced spring mass systems. And basically, a balanced spring mass system that, they extol the benefits of in engineering class is essentially, if you drop this on the spring and the damper, and everything's working in conjunction, it'll have the minimum amount of motion for the disturbance. So basically, imagine picking a car up, dropping a car, and as you drop the body on the suspension, obviously it travels past its at-rest point. So a car usually sits with we'll say 6 inches of ground clearance. If a real strong guy lifted the back of the car up and he dropped that car, the back of that car might go down to 4 inches. Well, if this car was in an engineering terminology perfectly balanced, that car would drop down and it might go to 4 inches, and then obviously the suspension is going to rebound to its at-rest position. Well, if it rebounds and comes right exactly to 6 inches, which is the rest point, it doesn't go any further, and it does that as quickly as possible. So if a system is underdamped in a traditional spring mass system, it would be closer to not having a damper at all. So basically, you pick the car up, you drop the car, and the car continues to bounce up and down. And, it would, you pick it up, you drop it, it would go down to the 4 inches, or might even go to 3 inches or 3.5 inches, and then it would come back, and instead of coming back to 6 inches, it would go up to 7 inches, and then it might drop down again, and it would drop down to 4.5 inches, and it would eventually, come back to that same rest point, because a damper works from in relation to velocity, not to position, in a theoretical damper. And an overdamped system is the opposite. You know, if you had a system that was so overdamped, you know, you could literally pick it up, drop it, and it may not even move barely, because there's so much resistance to motion that when you pick the suspension up and you drop it down, well, it's like dropping on, you know, it's literally, it either doesn't move, or if you were to take that same suspension system and you put a bunch of weight on the back of the car, so, you know, that heavy guy, that big strong guy that was lifting the back of the car, now he just sits on the trunk and he brings the suspension, you know, down to the 4 inches off the ground. Well, when he gets off, that car doesn't just come back to 6 inches in a reasonable amount of time, or the same amount of time, that perfect system. It slowly comes up, and the suspension kind of gets stuck down in its travel, and it takes, you know, 2 minutes for it to slowly get back to its that rest position. That's an overdamped spring mass system. Once you get into velocity and you know, other stuff, dampers get very complicated. Nothing is simple. You know, springs still remain relatively simple, but when we get into, you know, these fancy computer controlled suspensions in off-road vehicles, and this is really where I want to kind of get someone's wheels moving. You know, most of what I see is intelligent suspension means playing with damping. It never, I shouldn't say never, but I haven't seen many cases where people are playing with spring rates. They're you know, either, you know, you could have a spring in a car where you know, you have a lead screw on top of it or some other mechanism, and if you don't want body roll, you just compress that spring and you change, you know, the preload on the spring. And in addition, you know, obviously if you change that, you'd also have to change, possibly if you change the spring rate, you have to change the damper too, so they work together. But more interesting is actually, you know, and where I get, you know, kind of into it is for off-road or marine applications, because you get to a point where you can read the terrain. So, you know, we'll say we're running on the water. Now imagine a land vehicle with wheels that rides on the water. You know, we'll be a little creative. And when you're on the water, well, your chop often has a pretty consistent frequency. So if you can read the water and you can see you have X amount of chop, and you know, we'll throw a truck that rides on the water, because we're crazy, you know, some crazy people do. So there's your truck that rides on the water, and if your theoretical truck, you know, has lots of suspension travel, and you know, we're very lucky in that our theoretical truck, you know, has almost no mass to suspension, so these wheels that, you know, magically drive on water also don't have mass. You know, we're really fortunate guys over here. Well, we'll say the truck itself weighs 1,000 pounds. Or, you know, you like light trucks. The love truck. Who doesn't love a little love? And this mass, you know, there's no mass to the suspension, so it's just going to follow the, you know, the water. Well, remember that theoretical shock I had? That, you know, that air piston with that, if an air piston has an infinite volume of air, it runs with a straight rate. Well, if you have a, you know, the spring that's holding the truck up isn't a traditional coil spring, but it's that air spring that, you know, has, you know, basically no travel. Well, if there's 1,000 pounds holding this vehicle up, and there's no mass to this wheel, you can have this truck riding along the water. Yeah, we're having fun. We're really taking, you know, we're being greedy with the analogies. But essentially, this wheel is going to follow the path. And this truck, as long as the truck weighs 1,000 pounds and it's not accelerating or decelerating, it's just riding at a constant speed, it won't go up, it won't go down, it'll travel smooth as silk, even as the wheel, you know, fluctuates up and down, because there's 1,000 pounds, well, you know, on each corner, we'll say there's 250 pounds of force exerted, regardless of where the wheel is in its suspension travel. It's the same 250 pounds, and of course, the truck is balanced on each, you know, contact patch too. You know, not realistic, no, not really, but it's to get the point that the ultimate suspension system actually doesn't have damping necessarily. You know, if you can have the right amount of force at the right time and change that force, you don't need damping. Like damping, like I say, it's a band-aid, but kind of is. And the more you get into suspensions on you and dynamics, you know, things get interesting. And I'm not the expert in these matters, but I kind of want to just broach the subject, get these concepts out there, get the wheels in motion, and sort of expose people, because I don't see much of this. And again, there's all kinds of, you know, ways you can generate these kind of systems. Like, I have a particular, you know, recreational sporting device that needs a spring system that's similar to what I'm showing you, and that's one of the reasons it's been on my thought. But you know, that same truck, you know, it seems like, well, obviously, yeah, you got this giant, you know, mass of air, and you got this air piston, you know, so yeah, it gives you this you know, damn near, you know, straight, you know, consistent, you know, force up or down. But you know what? It's not that hard, you know, to have a linkage where, you know, okay, you know, there's a movable pivot in here, and depending on where the pivot is, you know, you move this pivot, and you know, if the pivot's, you know, close, well, guess what? You know, you have mechanical advantage, you know, in the lever arm, so that if you lock the pivot here, you know, you push down, and you know, it's you know, we'll say it's 4-to-1. So you know, if it takes 10 pounds of force to move this an inch, well, you know, 2.5 pounds. Now, you know, you move that pivot, you know, you can put a, you know, gear rack or something, a servo motor. But regardless, you can make a system where, you know, you can have it, this, you know, to move, you know, this eyelet up or down is anywhere from 2.5 pounds consistent to 10 pounds, or maybe 20 pounds. Just make an example, but it's like, this is the kind of thing that you know, I find interesting, because lots of people, like, it's easy to turn damping on and off and close orifices and open valves and go in that direction, but I don't see a lot of people playing with, you know, actually changing the spring rates or changing, you know, just the load of the springs. You know, I see very little of that, and I think there's a ton of potential there to play. And it's the kind of thing that you can play with without spending a ton of money. You know, you can buy lots of cheap shocks, and you know, you can pull springs off of, you know, junk vehicles. Like, this stuff is all readily available. So I want to do more and more of that, you know, in this shop. I mean, one of the things that I always laugh at, and you know, this zero personal interest in this stuff, but the fucking lowrider guys, you look at what they're doing, and it's like, God. Getting back to, you know, stored energy and hydraulic accumulators, why in the hell is there no lowrider with a PTO drive driving a hydraulic pump and then giant hydraulic accumulator, you know, and hydraulic systems? Like, you know, I have no business, you know, giving a talk on hydraulic systems. Every time I work with hydraulics, I curse my life. But essentially, what a hydraulic accumulator is, it's, you know, it's not so different from what we're discussing. Imagine a pressure vessel, and it has a, you know, a bag in the pressure vessel, just a rubber bag. So we'll say, you know, pressure vessel has, you know, there's 1,000, you know, pounds of force per square inch. In the pressure vessel. Well, what a hydraulic accumulator does is it pumps hydraulic oil into the bag. Now, obviously, gas is compressible, hydraulic fluid is not. So, you know, when you just let it go to rest, the bag compresses, and you know, all the hydraulic fuel is pumped out. But a hydraulic pump, you know, has, if you know, get it running, it's going to pump hydraulic fluid in there, and you know, it'll fill this whole mass with hydraulic fluid. And at a certain point, you know, it'll raise the pressure in the tank, you know, commensurate with the volume. But the fact is, you wind up with, you know, a good volume of hydraulic fluid at pressure, and it's, you know, essentially it's a very useful, you know, bomb. It's energy storage, and if you had a PTO drive, instead of having a bunch of little DC motors turning little hydraulic pumps with, you know, no energy storage. Your energy storage is in the form of, you know, 12-volt batteries. It's fucking asinine. You know, all the low rider guys should just have a PTO drive that uses the engine, which, you know, they usually have these small block Chevys or something like that. Well, you know, instead of having these dinky little motors, they could have a real hydraulic pump, like, you know, the one that, you know, lifts up the back of a wrecker or pulls, you know, winches cars up, and you could have that thing, you know, storing tons and tons of, you know, energy in the form of a hydraulic accumulator. So when you hit the buttons, you know, you just release this, and yeah, you could have a truck that'll, you know, bounce 30 feet in the air, and you know, you won't be spending all your money on hydraulic, on batteries and little motors that get hot and catch fire and all that nonsense. But I don't really, you know, the low rider guys, you know, they're paint workers, so I don't know, but I don't have that much interest in low riders. Except that I do have a little with one of the boating ideas. But again, we're not going to go there. We're just going to say that spring mass systems, lots of potential. I don't see it exploit a whole lot, and I'm sure there'll be comments. We'll digest them, and I'll see you guys later. Bye.